Well, good morning, everyone. My name is Arthur Carty. I'm the Executive Director of the Waterloo Institute for Nanotechnology. And it's a pleasure to introduce Dr. Mark Matsen, who is Professor of Mathematical Physics at the University of Reading in England for this WIN seminar. Professor Matsen is a Canadian who did his BSc in Physics and Mathematics at Simon Fraser University, winning the Governor-General's Gold Medal for the highest GPA in SFU's entire 1986-87 graduating class. He was an ENSO postgraduate scholar in our own GWP squared, Waterloo Program for Graduate in Physics, completing a PhD with Don Sullivan at Guelph before moving first to the University of Washington, then to the University of Minnesota for postdoctoral work on modeling complex fluids and block copolymer melts. He joined Reading in 1996 as a lecturer in physics and was promoted to reader in 2000 to professor in 2005. He then moved to the polymer theory group in applied math in 2006. Dr. Matsen is an expert on the assembly, architecture, properties, and behavior of polymeric materials, particularly block copolymers, polymer melts, and polymer blends. He is an authority on the development of SCFT, that's self-consistent field theory methods to model and predict the structure and behavior of complex polymers. I think his work on block copolymers and polymer brushes in particular will be of interest to polymer scientists and engineers here at Waterloo. And his recent research on charged polymers, for example polyelectrolytes, liquid crystalline polymers, and nanopolymers has commercial relevance in areas such as high energy density batteries and nanocomposite materials. Block copolymers, of course, are also of significant interest in targeted drug delivery via nanoparticles. Dr. Matsen has more than 100 publications, over 6,000 citations, and a Hirsch index of 37. He is well funded by the Engineering and Physical Sciences Research Council in the UK and has established very productive research collaborations with several other scientists at British universities, including Reading. Professor Matsen was elected a Fellow of the American Physical Society, APS, in 2008 for his seminal contributions to the development and implementation of a self-consistent field theory for copolymer materials and polymeric brushes. So please give a warm welcome to Professor Mark Matsen, who will speak about ultra-low friction between surfaces coated with polyelectrolyte brushes. Mark?
Thank you very much. Thanks for those kind words. It's very nice to come back to Waterloo. I didn't spend a lot of time here. I was mostly at Guelph. But you have a very nice institute. And it's a pleasure to come and talk about some of my research. My main area is block copolymers, but I'm not going to talk about this. I'm going to talk about research involving polymeric brushes. This is sort of a new area I'm entering. Some fascinating topics. It uses much the same theory. That's why it was relatively easy for me to enter this area. I'm going to talk just about one particular problem that caught my interest a few years ago. And it involves surfaces that are coated with charged polymers, polyelectrolyte brushes. And what was found experimentally is that if you coat surfaces with these charged polymers, that you pretty much eliminate friction. Quite an interesting result, and it was, at the time I started, still completely non-understood. So I'm not going to assume any prior knowledge about polymers. So, although I know many of you do work on polymers. So I'll start with just describing what a polymer brush is, how you create it, and some of the applications. And then, of course, I'm a theorist, so I'm going to try to model this, and I'll describe the model, how you apply theory to it. And I'll start by the simple case of neutral brushes, and then I'll move on to polyelectrolyte brushes with the aim of explaining this low friction. So just in case you don't know, what is a polymer brush and how do you create it? Well, a polymer brush is just ordinary polymer molecules attached by one end to a surface. And usually they're attached with a sufficiently large grafting densities that the molecules are very crowded and they're forced to stretch away from the surface, forming a film that's tens of nanometers thick. And the easiest way to create them is you just buy polymers with a functional end group, and you choose the end group appropriately, so that when you expose your surface to these polymers, the end group finds its way to the substrate and binds irreversibly. And the longer you wait, the higher the grafting density. When you're happy with your grafting density, you just wash away the excess polymer. Now, this works very well. It's very simple, as you can imagine. I could possibly do it. I don't know. The only problem is there's a limit on grafting density. Because once the brush gets thick, it's hard for new molecules to find the surface. So there's also an alternative way of doing it called the grafting from method. And this is where you lay down these red units without the polymers to start with. They're called initiator units. And because there's no polymers attached to them to start with, you can get almost any density you want. And then you expose the system to monomers, and the monomers will attach to the initiator, and then they'll start attaching to each other, and the polymer will grow. And then it's just a matter of waiting until you get the molecular weight you want. You terminate the reaction and wash away the monomers. The only problem with this method is you often end up with fairly polydispersed chain lengths. But if you don't care about that, this is an ideal method for creating high grafting densities. Now, there's lots of applications. I'm not going to try to tell you about all of them. I'll just mention some that I have worked on in the last few years. One useful application of polymer brushes is for creating repulsive forces. So if you take a surface and you attach this polymer brush to it, if you have a nanoparticle or maybe a protein molecule and it approaches the surface, if there's a polymer brush there, that compresses these molecules, it reduces their entropy, and that creates a repulsive interaction. So it's a very simple way of preventing nanoparticles from accumulating on a surface. Alternatively, you can attach the polymers to the nanoparticles themselves, and you can prevent the particles from sticking together, condensing. This is a fairly standard way of, I think it's a fairly standard way of stabilizing colloids. This is another sort of emerging topic in polymer brushes. It's a way of creating patterned surfaces. So instead of attaching just simple homopolymer chains, you can attach block copolymers. And this is one of my areas of interest, so it was natural I looked at this problem. So block copolymer is basically, unlike a homopolymer, it's where it's formed from two chemical species. So part of the molecule is formed from one species, and then the rest of the molecule from a chemically distinct species. And I just colored them blue and red. And then you attach these block copolymers to the surface. And the tendency, if you have two chemically distinct components, is they segregate. So by doing this, you get a chemically patterned surface. And you can change the geometry of the pattern by, for example, changing the composition of the dye block. Or you can expose it to different solvents or perhaps change temperature, and you can change the pattern on the surface. So you can get environmentally responsive surface patterns. And you don't actually have to graft the dye blocks to the surface to do this. There's a lot of work on forming patterned surfaces with free-floating films. But if you tether them, they form a much more robust film, and you can consider actually grafting them to nanoparticles. And there's a little bit of research going on. I have a collaboration with Ian Hamley, and he's doing the experiments for this at Reading. And we've done some of the theory. Now, today I'm going to be more interested in this problem here, where you have compression or repulsive force between two polymer brushes. And this is probably the best experimental work, or some of the earliest experimental work to really look at this was by Jacob Klein from Oxford. It was back in '88. He actually measured the repulsive force between compressed brushes. Several years later, in '94, he extended his experiments, and he also measured the frictional force. And what he found was that the friction is quite low. It's about friction coefficient of 0.1, compares quite closely to Teflon on Teflon. So these are very slippery surfaces. And that was published in '94. That was quite an interesting result on its own. But the really interesting result that caught my attention was this Nature paper in 2003, where he just repeated the same experiments, but this time with charged polyelectrolyte brushes. And the friction coefficient dropped by 2 orders of magnitude. So it's about 1% of that of Teflon. And there is really no explanation for why this happens. Now, I think this isn't surprising. It happens all the time, doesn't it? When you find something extraordinary like this, biology has already found it. Biology has been around far longer than we have. Actually, on the inside of your eyelids, you have polyelectrolyte brushes that allow your eyelid to slide smoothly over your eyeball. Also, on the surface of cartilage, there are charged protein molecules that form sort of a network that's sort of similar to this and responsible for lowering the friction between cartilage surfaces. Now, back at the time, it's a couple decades ago now, that people were looking at these neutral brushes, it was sort of understood quite well that the main source of friction was the collision between these polymer chains from opposing substrates or surfaces. And the reason for the low friction was because there was relatively little interpenetration between the brushes, and that was not too hard to explain, and I will explain that in a moment. So the implication is that somehow this charge is reducing the amount of interpenetration between the brushes and reducing the friction. So that's the idea, but there's no explanation why charge would do that. So that's where I entered. And now, because you're just interested in the interpenetration between the brushes, you don't have to consider two surfaces that are moving. You can consider a static case. And you can use equilibrium statistical mechanics, which is the type of theory that I work on. So the first thing is you have to, if you're going to do equilibrium statistical mechanics, is you need a model. Now, polymers are very high molecular weight and potentially difficult to model or computationally costly. But actually, the high molecular weight makes them easy to model, because you can take advantage of what's called coarse graining. So instead of trying to model the molecule at the atomistic level, what you do is you just consider the polymer chain as a smooth space curve, which I can specify by some function R of S, where S goes from 0 to 1 as I go from one end to the other end. And this molecule, I would imagine it as consisting of some number of end segments. And in the coarse-grained scale, a segment would look something like this. It would just be a straight line. And that's all you do in coarse graining. But if you are coarse graining, you still have to take into account the entropy associated with microscopic degrees of freedom. So if I magnify that segment to sort of the atomic scale, where I could start to see the atoms in the backbone, I would see that that polymer segment is actually a polymer coil. And that means you can actually stretch it. But as you stretch it, you lose entropy. That's because there are fewer and fewer configurations available to that coil as you stretch it. So you have to keep track of that. And it's actually fairly easy to do. The number of paths available to that coil is given by a normal distribution or a Gaussian function. It's just the normal distribution as it comes up in statistics for the exact same reason. And then entropy is the number of paths. So it follows that the entropy, which of course is proportional to free energy, changes as the length squared. So that segment behaves like an ideal spring. And the length, I can conveniently write that as the derivative of this space curve. And now if I combine all that, the entropy of that molecule for these microscopic degrees of freedom that I coarse-grained out is given by this simple expression here. So this is just the derivative of the space curve squared, and you integrate over the full length of the chain. And then I choose that constant C to be this, and that's just so that if you have an unperturbed molecule, thermal fluctuations will cause an end-to-end length of A n to the 1/2, and you identify A as a statistical segment length, which you can measure from experiment. So in a sense, what I'm doing is I'm modeling my polymer as a thin elastic thread where the elasticity comes from this entropy. And now the next step is I attach these elastic threads to two surfaces, and I form two opposing polymer brushes. And for the moment, I'm going to ignore charge. And when I form these two brushes, I'll have some polymer concentration. It might look like this, a little dip in the middle. And there'll be a background solvent that might look like that. And now I have to add in the molecular interactions. And for that, I think of Leonard-Jones type interactions where you have hardcore repulsion and attractive tail. I don't want to have to deal with the hardcore repulsion. So instead, the typical thing is you just say that the polymer concentration plus the solvent concentration has to equal 1 in some dimensionless units. So you assume incompressibility. And then all you have to consider are the attractive interactions. But on a coarse-grained scale, the range of the interactions is essentially nil. So you can model it as just contact forces. And as such, you can write down the energy in this form. So it's a contact energy between polymer segments, polymer concentration squared, and similar terms for polymer solvent and solvent-solvent interactions. And this expression is integrated over the volume of your system. Now, because I'm assuming incompressibility, I can get rid of phi s. I just replace it by 1 minus phi p. I can drop all constants because constants to the energy don't affect the statistical mechanics. I can drop integrals of phi p because that's also a constant. It's just the total amount of polymer. So in the end, you just have the only terms that are important are the phi p squared terms. And you collect them all up and you group these contact energies into a chi parameter. And you get this very simple expression for the energy. And it's quite convenient because it doesn't refer to the solvent degrees of freedom. It just refers to the concentration of the polymer. And to make life simpler, we'd like to get rid of the solvent altogether. But you have to remember solvent also has entropy. So there's one more step. You have to calculate the entropy of the solvent, which is just concentration log concentration. This is translational entropy. So I get rid of the solvent by writing it as 1 minus polymer concentration. And the last thing I'm going to do is, usually these brushes are quite dilute. They're mainly solvent. So phi p is small compared to 1. I can expand the log term in a Taylor series. And I just keep the most dominant term, the phi p squared term. And that's exactly the same form as the energy, so I can group it together. And so I rewrite my energy expression as this integral phi p squared. And I have a parameter v here, which will now be 1 minus 2 chi. So the 1 comes from the entropy of the solvent, and the 2 chi from the molecular interactions. And this parameter v is called the excluded volume parameter. And like any parameter, it can be positive or negative. Positive means that the solvent wants to swell the brush. Negative means that the brush wants to collapse. And the boundary between them is called the theta solvent condition. Normally, you're interested in the good solvent condition, where the solvent is swelling the brush. I'm also going to talk about the theta solvent condition when I come to polyelectrolytes. So this is the model. It's as simple as you can imagine. Elastic threads attached to a surface, and the interaction energy is given by this integral of the polymer concentration squared. So there's the system I want to model. And despite the simplicity of the model, I still can't do this exactly. The problem is there's just too many molecules. So the thing to do is, especially with polymers, is apply mean field theory. Works very well for large molecular weight molecules. So what I do is I just concentrate on one molecule, say this one, and I replace its interactions with the other molecules by an interaction with a field, the field W. Eventually, that field will have to be solved self-consistently, so it will have to be adjusted so that it's equal to this exclude volume parameter times the polymer concentration. So I just, for the moment, I'm dealing with a single polymer in a field W of Z. And then I can specify the configuration of this molecule by a function Z of S, which just tells me where the S segment is, how far it is from the substrate. And now it's not too hard to do statistical mechanics. I just need an energy or a Hamiltonian for that polymer. And my Hamiltonian is this one. So this is the stretching energy that I talked about because these polymers are treated as elastic threads. And then this is the interaction with the field. And once you have a Hamiltonian that tells you the energy for a given configuration of the molecule, you just do statistical mechanics, so which you calculate partition functions. So the partition function for a single molecule will be given by an integral like this. It's some Boltzmann weight. You integrate over all possible configurations of the molecule, and I need to include a delta function which graphs the s equal 1 segment to the z equals 0 plane. And that would be a partition function for the entire molecule. Now, I'm going to need to solve this equation up here. So I'm going to need to be able to calculate the polymer concentration. And to do that, I need more general partition functions than this. And I need what's called a propagator. It's very much the same as that partition function, but it's just for a fragment of chain. So from 0 to s primed. And I'm going to constrain both ends of the chain. So one end of the chain will be constrained to Z1, the other end to Z2. And then I consider all paths of that fragment between these 2 points, Z1 and Z2. And this is the partition function for it, or the propagator, so it depends on Z1, Z2, and the length of the fragment. And it's the same Boltzmann weight, but only for a fraction of the chain. And it has 2 delta functions because I'm constraining both ends. So once I calculate that, then I can do just about everything I need. In fact, I can do everything I need. For example, if I wanted that single chain partition function, it's just this propagator, but I set s prime to 1 because I want a full chain. If I want to graph my chain to the substrate, I set z2 to 0. And if I don't want this point to be fixed in space, I just sum over all allowed values of z1. And then I can get this single chain partition function. The thing is, with this, I can also calculate the segment concentrations, which I need. So to do that, I consider a chain that's actually constrained at 3 points. So what is normally the free end, I constrain it at Z1. And then some segment in the middle, segment S, I constrain at Z. And then this is the grafted end, which is constrained at the substrate, Z equals 0. And now I want to calculate the Boltzmann weight. I want to consider all polymer trajectories that satisfy these 3 constraints and calculate the probability of that, which is a Boltzmann weight. Now, these constraints divide the molecule into 2 portions. And I can calculate the Boltzmann weight of each portion. They're just the propagator that I was talking about. And then the Boltzmann weight for the entire molecule is just the product of these 2, because those 2 portions are uncorrelated. Because they just interact with the field, not with themselves or with each other. So you get this Boltzmann weight, and this Boltzmann weight is the probability distribution of segment S. But it's for a molecule that is constrained at both ends. And that's not quite what I want. I don't want the Z1 end to be constrained at all. But we know how to get rid of that constraint. We just integrate over Z1. So I take this Boltzmann weight, integrate over Z1. So I turn that into a free end. And I don't just want the concentration of segment S. I want the concentration of the entire molecule. So I simply integrate over S, S from 0 to 1. And then there's some proportionality factor. This is sigma is the grafting density, and that is the single chain partition function I was talking about. And this is the polymer concentration of the entire brush. Now, once you have that, then you're in business. You need to, so the field goes in, and you get the concentration out. And they won't satisfy this condition, so you have to adjust the field until you reach this condition. And there are different methods of doing that, different iterations. And you just iterate these equations, or do this calculation iteratively until you've satisfied this. And then you have the polymer concentration, which tells us the amount of interpenetration between the brush. So that will let me know something about the friction. I'm also going to want to know about the normal force. And for the normal force, you need free energy of the brush. Free energy is normally just log of the partition function, or minus log of the partition function. But this partition function here is for a chain in the field. If you consider a chain in the field, or all the chains in the field, what you're doing is you're double counting the internal energy. So you have to correct for that. So this is the free energy for polymers in the field. And then this, you subtract off the internal energy, and that corrects for double counting. So that's the mean field theory for a polymer brush. It's very straightforward. The only thing is I haven't told you how to calculate this propagator. Now, it turns out that actually calculating this propagator is exactly like doing quantum mechanics. So there's no sense in reinventing the wheel. We just look at the analogous problem in quantum mechanics. And the analogous problem is actually the simplest quantum mechanical problem you can do. Just consider a single particle of mass m moving in a one-dimensional potential u of x. Now, in quantum mechanics, what you want to calculate are wave functions. Normally, you would do this by the Schrödinger equation, but there's an alternative formalism developed by Richard Feynman. It's the path integral formalism. And conceptually, it's very simple to use. What you do is you just imagine some trajectory for this particle, call it x of t. If you differentiate x of t, you get the velocity. So this term right here, this is kinetic energy minus potential energy for some trajectory. That's called the Lagrangian. If you integrate the Lagrangian, then you get the action for your trajectory. And what Richard Feynman realized is that if you take e to the I, where I is the square root of -1, times the action and divide by Planck's constant h bar, and then integrate over all possible paths of that particle, you end up with the wave function. So that's the path integral formalism. And then you calculate whatever you want. The thing to recognize is that doing that is exactly the same as calculating a partition function for a single chain in a field. This is the propagator. It's given by an integral like this. And h is the energy of the polymer. And the energy of the polymer is the stretching energy, because I think of it as an elastic thread, and the interaction with the field. And if you look, it's exactly the same. This stretching energy is just like kinetic energy, and the field is like the potential, and the propagator is like the wave function. There are some subtle differences. There's a plus sign here instead of a minus sign. There's no I in the exponential. Of course, that completely changes behavior. But it doesn't change the mathematics. The mathematics remains identical. So if I can map these two problems onto each other, I can just steal the mathematics from quantum mechanics. So this is the mapping. So you map time onto the parameter along the polymer chain. The two trajectories map onto each other. The mass of the particle maps onto this quantity here. The potential maps onto minus the field. H bar maps onto temperature. Action onto energy. Wave function onto propagator. Now, if you have done quantum mechanics, you know that you don't usually use the path integral formalism to calculate the wave function. You use Schrödinger's wave equation. And this is Schrödinger's wave equation. So I'm going to do the same thing to get my propagator. All I'm going to do is take this wave equation, make all these substitutions, and I'll get an equation for the propagator. And this is the equation that comes up. It looks very similar. It's not a wave equation anymore because there's no I here. So it's actually a diffusion equation. But mathematically, you solve it in the same way. So this is the way you get the propagator. Now, this analogy has another benefit as well. We know in quantum mechanics that if h bar goes to 0, you get classical mechanics. And from this correspondence, we know that classical mechanics is going to correspond to the 0 temperature approximation of my polymer in a field. And the nice thing about this is that can be done analytically, paper and pen. So let's just work out the 0 temperature approximation of the polymer brush. So this is my polymer in a field. The s equals 0 segment somewhere out here, and s equals 1 is grafted to the surface. So I have these two conditions. And remember also the derivative of the space curve is the tension. It's the amount the polymer segment is stretched, and the amount it's stretched is just the tension because it's an ideal spring. So Z primed is the tension. And at the free end, you can't have any tension. The free end can't support tension. So you have a boundary condition. Z primed at the free end has to be 0. So now we map this onto the particle in a potential. And the 0 tension at the free end means I'm going to start the particle from rest, because Z prime corresponds to velocity in this problem. So I start a particle from rest at some arbitrary point and then in 1 unit of time, I end up at x equals 0, regardless of where I start the particle from. And if you've done any classical mechanics, you'll realize I've just described a simple harmonic oscillator. More specifically, I've described the simple harmonic oscillator with a period of 4, because what I've described was 1/4 of a period. So I know precisely what that potential is, and I can map it back into the polymer problem. And I get that the field has to be an upside-down parabola, because there was a minus, U was related to minus W. And then there's some constant which I can't figure out because constants don't affect the trajectory. I'll have to figure that out later. And the trajectory, because it's a simple harmonic oscillator, is just a simple cosine function. So the nice thing about this is I've got this self-consistent field without having to solve a self-consistent condition. I just know that my polymer brush has to adjust itself to be parabolic, because that's the only allowed field. Now, there's one little additional thing I need, one little complication, is eventually I have to calculate the stretching energy, not of just this chain, but all the chains in the brush. And now, the stretching energy for a single chain would be given by this expression. So that's the tension squared integrated over the length of the molecule. And of course, this is the trajectory. I could just differentiate that and plug it in. But it depends on this endpoint. So this is the position of that s equals 0 segment. And different polymers will have different values of Z0. And I don't want to have to calculate the distribution. So I use a little trick. It's the virial theorem from classical mechanics, which says for a simple harmonic oscillator, the integral of kinetic energy is minus the integral of potential energy. And so this term, this integral, which is like the integral of kinetic energy, can be written as the integral of potential energy. And that's but the potential, so I get Z squared here. And then the next step is, instead of integrating over S, I'll integrate over Z. So that's a change of coordinates, and that here you would get a ds dz, which is an amount of polymer over a volume, so that's a concentration. And so it would be ds dz if I'm dealing with a single polymer. But if I want to sum over all polymers, because it's linear, when I sum over all polymers, that ds dz will turn into the total concentration of the brush. So this last expression here gives you the stretching energy of all the chains in the brush. And with that, I'm in business. I can do the calculation very quickly. I'll start with the simplest problem. So this is still neutral brushes. I haven't added the charge in yet. I know that the polymer concentration is proportional to the field. As I argued, the field is parabolic. It involves some unknown constant, which I call L squared. But I can interpret L as the height of my brush. So my brush profile looks like this. So this is the substrate, and the polymer concentration drops off as you go out. And at some point, there are no segments. And I have to determine this constant. Well, what we know is that the area under the curve is just the amount of polymer. So there's this condition here. The amount of polymer is related to the grafting density. And then I can use that to solve for L, and I get this nice expression for the height of a polymer brush. Then I plug that back in, and once I know the polymer concentration, I can calculate the free energy. That's the stretching energy term I just derived, and that's the molecular interactions, the internal energy. And you can integrate a parabola, anyone can do it, and you get that simple expression. Now, I'm actually interested in compressing brushes. So when you compress brushes, the brush won't be able to go out to some height L. It will be compressed to some height D. This argument about the parabolic shape still is true. So the polymer concentration will drop off parabolically. And then once you get to D, it just has to go automatically to 0. And because I know the amount of area under the curve is conserved, because I don't lose any polymer, I can work out what this concentration is. And I can plug it into this expression, and I can do the integral again. It's still a parabola. And you get this expression. So this is the free energy for a compressed brush. And it's the free energy of the uncompressed brush times this analytical expression here. Now, you would think this is too simple to work. Well, it actually works quite well. So I mentioned that the first experiments to measure the compression force between two brushes was done by Jacob Klein. It's his '88 paper. It's quite famous. He looked at polystyrene brushes in toluene solvent. And these are the parameters from his experiment. So his polymers had 1,360 segments. The segment length is this. This is the grafting density. And the excluded volume parameter for polystyrene in toluene has a literature value of 33.7. And I can just plug all these numbers into the simple zero temperature approximation of a brush, and I get a parabolic profile with a height of 660 angstroms. And if I take two opposing brushes and provide the two plates are far enough apart that the brushes don't touch, their profiles won't be perturbed, and there'll be no force between them. The force will only occur when I bring the brushes together and I compress them, and you'll get these compressed profiles. And the theory predicts that once the brushes touch, they will start contracting. So the zero temperature theory predicts absolutely no interpenetration between the brushes, and that's why the friction between neutral brushes is quite low. Of course, this is only the zero temperature approximation. Now, when the brushes are compressed, of course, the free energy goes up, and that means there will be a normal force between these brushes. And if they were planar surfaces, you would just differentiate the free energy and you would get the force. But actually, it's very hard to align parallel plates, so the experiments are done with crossed cylinders. You take two large cylinders at right angles and you bring them together. And in that case, you can show, as long as the radius of the cylinders is large, and it's about 1 centimeter for his experiments, that the normal force between these cross cylinders is the radius times the free energy. So it's actually a very simple expression. So in the experiments, what they plot is normal force divided by the radius of the cylinders, and they plot it as the separation between the cylinders. And this is the experimental data. The open and closed circles are for loading and unloading, or bringing the cylinders together and then apart. And the fact that they overlap means there's no real hysteresis, and I can legitimately use an equilibrium theory. And this ratio should just be the free energy. So if I use the zero temperature approximation, the free energy was given by a simple expression, analytical expression like this. And if I plot it, I get this curve. And it works quite well. And I must stress there's not a single fitting parameter in here. This is just using the parameters from the experiment. Now, this is a log scale, so that difference is actually a factor of 2. So the theory is underestimating the normal force by a factor of 2. Considering the simplicity, that is pretty good. Now, of course, I have the full theory, the finite temperature theory, self-consistent field theory. And so I can repeat this all with self-consistent field theory, and that's the red curves here. So if you do it for finite temperature, you get the parabolic profiles are altered a bit. The main effect is you get these fluctuation-induced tails. And in this case, the tails from the two brushes would overlap or interpenetrate, which would lead to friction. And also, it would produce a slight normal force between these two brushes. If I bring the two plates together, the brushes still contract, as the zero temperature approximation suggests. But nevertheless, the interpenetration does increase, and there would be a stronger normal force. And I can calculate it. After all, it's just free energy. And from the self-consistent field theory, I had an expression for calculating the free energy. And this is the comparison. I have two calculations here. The dashed red curve is where I assume that these polymer chains are monodispersed. They all have whatever it was. I forget the number. But they all have the same molecular weight. But that's not actually correct. There was some polydispersity, and it was reported to have a polydispersity index of 1.02. If you work with polymers, you know what that means. Anyway, I can include the polydispersity in the calculation. And if I do, I get the solid red curve. And again, not a single fitting parameter. This is just the parameters from the model, or from the experiment. And so it nicely goes through the data. OK, that's neutral brushes. Okay? So that's all explained very nicely. The big question is, what happens when you charge the polymers? So if I charge the polymers, I'm going to imagine that I'm going to put my polymers in a salt solution. So there's extra parameters. I'm going to have to specify how many charges on the polymer. I'll call that NC. I'll have to say what the salt concentration is. That's going to be my phi s. And because now there's electric charge, there's electrostatic interactions, I have to say how strong the electrostatic interactions are compared to the thermal energy, for example. And this is usually done by specifying what's called the Barham length. And basically, it's the distance between two monovalent ions at which point the electrostatic energy exactly matches the thermal energy kT. But anyway, it doesn't matter. The Barham length is just directly proportional to the strength of the electromagnetic interactions. Anyway, we've got 3 more parameters. I already had oodles of parameters for the neutral brush. So at this point, I'm just going to switch to dimensionless quantities. So for Z and D, the distance from the substrate and the separation of the plates, I'll just divide by the natural size of a polymer molecule, so I'll get dimensionless distances. It also turns out for semi-dilute brushes, which is what I've been working with, you can scale out the effect on grafting density. If I just take my excluded volume parameter, multiply by grafting density, and the Barham length multiplied by grafting density, and then for the concentrations I divide by grafting density, I get these quantities here where all the dependence on sigma, the grafting density, has been scaled out. And I'll also have a dimensionless version of the electrostatic potential, which I get from multiplying by E, the electronic charge, and dividing by kT. So I'll work with these quantities here. So how does the theory change when I charge my polymers? I'll deal with self-consistent field theory first, because that's the easy one. So now for the neutral brushes, the field was the excluded volume parameter times the polymer concentration. Now, when my polymers are charged, that means they also interact with the electrostatic potential. So all you do is you gain this extra term on the field. And you also have to solve for the electrostatic potential. But that's just solving Maxwell's equation. Divergence of the electric field is charge density over the electric permittivity of the solvent. And for a one-dimensional problem, Maxwell's equation is simply this. This is the divergence of the electric field is the second derivative of the potential, and the charge, there's positive charge on the polymer, and then negative charge from the minus ions and positive charge from the positive ions. So this is just Maxwell's equation. It's called the Poisson-Boltzmann equation in polyelectrolytes because the concentrations of the free ions are given by this Boltzmann term. This is basically just assuming that the ions only interact with the electrostatic field. And then this is the salt concentration. So that's all you have to do to include the charge in the self-consistent field theory. And you're doing it numerically anyway, so this is no added complication. It does, however, mess up the zero temperature approximation, which is a shame because that's an analytical theory. So in the zero temperature approximation, the field was parabolic. And that's still true. But I was using the fact that the field was parabolic to imply that the concentration was parabolic, which was true for neutral brushes. But when I have this term, it doesn't work anymore. So what's generally the case is, for strong polyelectrolytes, is the electrostatic interactions dominate the enthalpic interactions. So what I'll do is I'll just turn off this term here, which technically means I'm going to consider the theta solvent condition. And if you turn off this term, then that means the electrostatic potential will have to be parabolic. So the brush will do whatever it needs to make the electrostatic potential parabolic inside the brushes. And then I can differentiate this twice. Anyone can differentiate a parabola. You plug it in there. You solve for the polymer concentration. And you get this nice analytical expression. And you're in business again. There's a fair bit of mathematics, but it's all analytical, paper and pen again. I'll just show you the results. So this is results for the zero temperature limit. I'm going to consider the case where there's no salt. So it's just brushes in pure water. You have the charged brushes and their counter ions. And I'm starting with isolated brushes. Now, it turns out not only can you scale out the dependence on the grafting density, you can also, in this theory, scale out the dependence on the number of charges per polymer chain. So if I multiply polymer concentration by number of charges to the 1/2 power and divide Z by NC to the 1/2 power, multiply the Barham length by NC to the 3/2 power, I scale out the dependence of the number of charges. And the whole behavior is just controlled by this one reduced parameter, which is basically the strength of the electromagnetic interactions. So when this value is small, you might have a brush profile that looks like this. You increase the strength of the electromagnetic force, and the polymer stretches, and you get a profile like this. And if you plot the average height of that profile, as I ramp up the electrostatic interactions, you get a curve that looks like this. And there's two scaling regimes. One's called the Pincus regime, and one called the osmotic regime. So this is where the electrostatic interaction is so small that the ions just escape from the brush. And then once you increase the electromagnetic attraction, then the ions are pulled back into the brush, and you get this osmotic regime. Turns out experiments observe this all the time. This, as far as I know, has never been observed. OK, I can, of course, improve upon the zero temperature approximation by doing self-consistent field theory. You get similar profiles again, but there are these tails to the profile. And the size of the tail depends on how many charges is on each of the polymers. So I've done a couple. As the number of charges on the polymer increases, you go towards this zero temperature approximation. And if I then plot the average height of the brush, of course, the tails will make the average height larger. I get these red curves that are above the blue curve. And here I'm plotting them for different values of electromagnetic interaction. And they all nicely collapse in the osmotic regime. They don't here. This nicely explains why no one ever observes the Pincus regime. OK. Now, of course, I'm not interested in isolated brushes. I'm interested in the compressed brushes. This is the million-dollar question. So here, this is still without salt. Two pretty isolated brushes far apart. Now, if I start to compress them together, this is the zero temperature approximation, this gap closes, but it closes. I press more, it closes even further. But there's always a gap. And if you think about it for a second, that's why the friction is so low. This is in complete contrast to the neutral brushes. What happened in the neutral brushes, if you bring them together, they don't change until they actually touch each other. Then they start contracting. What happens when you have charged brushes is they start contracting before they even touch. Well, that's in the zero temperature approximation. Of course, they do eventually touch. If you do the full self-consistent field calculation, so you get these little tails, and it depends on how many charges the polymers have. And eventually, if you push hard enough, they are going to touch. Now, so the friction is concerned, supposedly, about the amount of interpenetration between these opposing brushes. So here's a calculation. This is sort of calculating the fraction of overlap between these two brushes. And I'm doing two calculations here. One is just an imaginary calculation. I take these profiles for isolated brushes, and I just bring them together. And I calculate the amount of overlap. And if I do that, I get this curve here. And I'll arbitrarily say, well, friction might start when I get 1% overlap. So this would be the point where you would start getting friction, when the brushes were at that separation. But the brushes do actually contract. So if I do the full calculation and allow them to contract, this is the interpenetration between the brushes. And this would be the point that they actually contact. So by contracting, I can bring the brushes closer together before the friction sets in. And why is that important? It's because as you're bringing the brushes together, the normal force, or the free energy, is going up. So this is the free energy curve, or the normal force between the brushes. And this is the normal force you would have if the brushes didn't contract. So this would be the normal force at the point where the friction set in. But because the brushes contract, you don't get friction until you're up at a much larger normal force. And that's the whole name of the game. You can always get low friction by holding your brushes apart. You want to be able to push on them hard with several atmospheres of pressure before you actually get friction. And it's basically the nice behavior, or the suggestion from the theory, is all because of this contraction of the brush, this polymer-free gap in the zero temperature approximation. Now, the theory is very nice. It tells you that there's this polymer-free gap. You have to dig a little bit to find out why, but it's an analytical theory, so you don't have to dig too hard. This is the profile that I've been drawing for an isolated brush, polymer concentration. I haven't been showing you what the concentration of counter ions looks like. In an osmotic brush, It almost matches the polymer concentration, but some of the ions leak out of the brush. And this will always happen because these ions gain entropy by occupying this space out here. Now, if I bring another brush up next to it, what I'm doing is I'm reducing the volume available to these ions. In this, I reduce their entropy. And if there's less entropy, then they just return to the brush. They screen the electrostatic interactions. And it's the electrostatic interactions that are stretching the brush. So when the ions return, the brush contracts. And that's why the brush contracts before they actually touch. Now, everything I've been doing is imagining, I can imagine I've done it in pure water. But in a lot of applications, biological applications, for example, you're doing this in an electrolyte with basically water with salt. And what salt does is it screens electrostatic interactions. So a potential fear is that you would lose this nice behavior as soon as you add salt to the system. The experiments haven't really been done yet, but this is just the last thing. What happens if I add salt? Well, if you add salt, that means out away from the brush, you have some ion concentration that's non-zero. That means fewer of the counter ions will leave the brush. So when you add salt, the brush will contract. But that's a good thing. Contraction means less interpenetration. The bad thing is that the range of the interaction is dictated by how long it takes for the ion concentration to reach the bulk value. The bulk value of here, or salt concentration, is 0, and here it's non-zero. So the range of the interaction is going to be shorter when you add salt. And that means the normal force will be smaller. And that's a bad thing. So it's just a question of how does it work out quantitatively? So I'll start with this. So this is the case for the neutral brush without salt, pure water. And this is where you would have contact if you had 25 charges on the chain or 100 charges. Now, if I add salt, the position of the contact points where the friction sets in goes like this. It's hardly affected at all by salt concentration. And then the question is, once the brushes do make contact, what is the normal force? And if I plot it, these are the curves you get. So as expected, salt reduces the behavior, or degrades the behavior. The normal force drops as you increase the salt concentration. But the saving grace is that this is a log scale. This is only a linear scale. So actually, you can add a lot of salt before you lose a normal force. Now, I'll stop here. I know I've used up my time. And besides, it's time for the experimentals to have a look at this. So that's just my conclusions. And I'll let you read them because I know I've gone over. Okay?
Time for a few questions?
Sure. Yeah. Sure. Yeah. Of course, the experiments are done on flexible polymers, and the model specifically refers to flexible polymers. So it is very much a theory for flexible polymers.
Push it when the persistence length becomes.
Yeah. Yeah. So yeah, but the zero temperature calculation would be pretty much impossible to do with the persistence length. But the self-consistent field theory can easily be done with the persistence length. So if I wanted, I could try the calculation again with semi-flexible polymers.
And have people done quantum experiments where they use rigid polymers? Because
No,
that should be observable.
Yeah.
This type of experiment.
No, there's very few experiments on this. I think there's the original experiments by Jacob Klein in 2003, and then they've been done with a different system. And actually, it's another thing that's important is it has to be a strong polyelectrolyte where all the ions dissociate. There's also weak polyelectrolytes where you get partial dissociation, and you don't get the low friction for that. And I haven't done the calculation. It's sort of in the back of my mind. If I have time, maybe I'd look at weak polyelectrolytes. So there are a lot of issues, like you say, the flexibility of the polymer coil, whether it's a strong polyelectrolyte, weak polyelectrolyte. Yeah, so it's a good question. I couldn't tell you what the answer is right now. And the experiments haven't been done.
I was surprised that the grafting density scaled out.
Yeah.
Is that because the electric field or the electrostatic follows the grafting density, or?
It only works for low grafting densities or semi-dilute brushes. So that's why I considered semi-dilute brushes, because it's a nice result that the grafting density scales out and you get one less parameter that you have to worry about. But, and for the self-consistent field theory, again, no problem if you want to look beyond, say, more dense brush. It's easy. For the zero temperature approximation or strong stretching theory, you can't do it analytically if you go beyond semi-dilute.
Yes?
Well, I have two questions. The first one might be a very naive one, because you mentioned the analog between the integral interpretation of quantum mechanics and the polymer theory. And we know that in order to solve many electron systems in quantum chemistry, we sometimes use some self-consistent numerical methods, such like
Hartree-Fock, yeah.
So is there any analog between those methods and your SCFT?
Yeah, I mean, there are other problems where you can take advantage of this analog. There's one probably not in this polymer problem, but other polymer problems where you use self-consistent field theory, you can. Antron Shi at McMaster has done a nice one where he looks at block copolymer structures that are periodic, and he looks at thermal fluctuations away from the mean field solution. And that corresponds exactly to doing band structure calculations. So all the mathematics from band structure calculations can be used to solve that polymer problem. There's also some work that I'm much less familiar with by Dave Morse, where he's expanding beyond mean field theory. And this is sort of more like Feynman diagrams and that type of expansion. But yeah, and then there's also computational methods that are similar between.
Another question of mine is, when you mentioned adding salt to between your polyelectrolyte chains, are these salts just monovalent? For example, if your polyelectrolyte chain carries positive charge, what if we have divalent counterions, such like SO4 groups? If you add that into it, how would it alter the entire picture?
It's very straightforward. Yeah, I just chose monovalent, but you can add that in. It's no complication. Yeah.
You were considering polyelectrolyte brushes between planar surfaces.
Yeah.
Have you thought about a surface which has the topology patterned on a nanoscale? And for the case of polyelectrolyte brushes, would there be any advantage or disadvantage to doing that?
Now you're not talking about friction. Oh, talking about friction.
Let's say.
Oh, if.
Or normal force.
So the surface is just chemically modified, but it's still flat, you say.
Imagine, let's say that you had maybe two heights or something, pillars, let's say.
Yeah, well.
I'm just wondering, would it be better or worse? Do you know?
I'd expect it would be worse. I think you'd be better with a flat surface. But, I mean, numerically, you could do it with self-consistent field theory. It'd make everything somewhat more complicated, because the electromagnetism is a lot easier to solve in one dimension. But there's no problem when you do it numerically. It's certainly a feasible calculation. I expect it would, you get better.
How about roughness, let's say, if you thought about that?
Yeah, you could look at it. It's not at the top of my agenda, but it's certainly something that the theory could access. The self-consistent field theory is very flexible. You can do all these type of things. The zero temperature approximation is, if you deviate too much from special cases, then it just becomes intractable. But as long as you're happy to do numerical calculations, the theory is very versatile.
Let me ask something a little bit beyond this. So, biology likes Switzer ionic systems. So, if you would have, instead of
deuterionic groups along the chain. That how do you expect this to be modified? I can imagine that there would be hydration effects and stuff that would just sustain pressure.
Yeah. Yeah, I'm not sure. I'd have to think about how to. Being a coarse-grained model, it sort of is somewhat limiting in that respect. So you have to think about how you could sort of mimic it, I guess. I couldn't do that off the top of my head. I'd have to give it a little bit of thought. But yeah, there are experiments on this. I think Jacob Klein is also looking at such systems. Yeah. Yeah, Rob? Well, the reason I did polydispersity is because this calculation was done by Milner quite a while ago. And he couldn't get it to match the experiment. He actually tried to push up all the parameters to, like, grafting density to the limit that he could. And then when he did add polydispersity in the zero temperature approximation, it had a big effect. And he did get pretty close to the experimental result. But he had to add in polydispersity, and he had to push the limits on the experimental estimates of grafting density. The effect is much smaller in self-consistent field theory, and you have to trust self-consistent field theory over the zero temperature approximation. But what's just happening here is that if you have polydispersity, you know, in block copolymers, polydispersity lowers the stretching energy. You can fill space more easily. Of course, you use that idea in melts, but it also works in solution. So basically, if it's polydispersed, the brush height increases, and thus the force sets in sooner. And that's just why the curve moves up a little bit.
Michael?
Very interesting talk. Can you show me your, I think, slide 5 slides from the back, where you show the...
From the back, so still going
forward.
What am I doing? Yeah. One more?
One more? Yeah, this one.
Okay.
So this actual graph, is it due to the fact that if you bring the brushes together, the interaction forces causes the counter ion to be expelled, that causes the reduction in the chain length? Is that what?
Yeah, no, okay. Yeah, maybe this is the key point, so I explained this a little bit more. So these are the two opposing brushes. They're stretched by the fact that there's more positive charge here than negative charge, so they stretch. And the excess counter ions are sitting out here because they gain entropy by, and now as I bring the brushes together, the entropy you gain by occupying this volume is reduced because there's less volume. So then the counter ions return to the brush because the brush has a positive, well, it has some positive charge and the counter ions are attracted to it. So if there's no entropy to be gained by being out here, then they'd like to be back in the brush. And then that screens the electrostatic interactions and the brush collapses. So as you try to bring them together, the ions enter the brush and screen the interactions, and the brush just keeps contracting, always leaving this polymer-free gap. Yeah?
I was wondering how the presence of a charged grafting surface would affect the dispersion of the polymer and the friction. Something like silicon.
Yeah. Well, there are, actually, that was a problem I was interested in before. Not looking at two compressed brushes, but actually the problem I started with was I was interested in charging the surface, the grafting surface, and you can either positively or negatively charge it and compress or expand the brush, or it compresses. And there are experiments done by Richard Jones' group in Sheffield that were looking at that. I got sidetracked onto this. But yeah, you can do the calculations. You can, I'm pretty certain that if the polymer is positively charged and you charge this plate positively, the brush will stretch. And if you negatively charge it, it will compress. But it's not symmetric. But it's a problem I might want to return to. It's a little bit complicated. You get violations in this parabolic field. I gave the argument, but there is sort of a caveat to that argument. It assumes that chain ends are everywhere. So in my analogy, I said I could start from anywhere and I have to get to the substrate in 1 unit of time. That's true if the polymer ends are everywhere, but if they're not, then you don't have to have a parabolic shape. And this sort of is well known. You get something called dead zones. So normally there's chains of all different lengths here, or stretched to various degrees, and there's ends everywhere in there. If you charge the plates, what happens is all the ends go, well, if you positively charge it, and all the polymers will stretch, there'll be a dead zone here. And that just makes the calculation a little bit more complicated. You can do everything numerically, though. It's an interesting question. There are experiments that have looked at this, so the theory could certainly handle it.
One last question.
What about if you have a die block? Let's say the substrate is here, you have a charge and neutral, or neutral and charge. How would the behavior differ?
Charged and neutral.
Die block with a charged segment, and then the one that's free end is non-charged. Then you reverse it, you have a non-charged and a charged at the free end. Mm-hmm. How would the behavior
change?
Display,
I don't think I can answer these things right off the top of my head. Certainly. But these are all very accessible within the calculation. You can do them if you can imagine such problems that can easily be looked at. Maybe give me a few hours, I think about it.
Okay, I think things have run out. We'll stop here, and I'll ask you to join me in thanking Dr. Matsen for a very interesting talk.